Greetings, my people. I hope we're doing okay today. We're going to go ahead and get started on trig derivatives. As you might expect in this first one, I'm going to tell you / remind you of where these things come from, why they are, what they are, and all sorts of fun stuff like that. And of course, in order to do that, at least initially, I have to make recourse to the limit definition of a derivative. So if I am looking for the derivative of sine, right, that must be sine x plus h minus sine x, all of that over h, correct? Well, I think you've seen me do this before. Becomes sine x cosine h plus cosine x sine h minus sine x. And of course, to get from the first step to the second step, I simply use the sum formula from my trig identities, if you remember that from last year. If you don't, you need to. So go ahead and go back and rememorize those. You're going to be very, very happy that you did. Now, what I'm going to do is I'm actually going to start collecting these terms in a little different order. I'm going to rearrange them, and I'm going to send this negative sign over here and couple it up with this first term, sine x cosine h. Now, when I do that, I can actually go ahead and factor out a sine x, and then I'm just going to put the h just underneath the cosine expression. Now, I can do that, and if you don't understand the algebra behind that, I can, deal with that at another time. And this one winds up being cosine sine h over h. So all I did in this second term was I dealt with this term right here and simply pulled the cosine out because of the same principle that allows me to pull this sine out right here. Now, what you should notice here is that these two right here are those recognizable trig limits that you memorized by formula for the last chapter. And so what happens here is I get the limit as h approaches 0 of cosine h minus 1 over h times sine x. Now remember, this whole thing, I can pull sine x out. Now the reason I can pull sine x out is because with respect to the limit, everything that is not h is a constant, okay? And the same thing over here. I'm going to have the limit as h approaches 0 of sine h over h times cosine x. Now remember that the formula as it was originally given to you was actually 1 minus cosine h, not cosine h minus 1. But it was for 0, right? So what happens if I have a difference equal to 0 and then I flip it around? Well, it's still equal to 0, right? So that winds up becoming 0. That winds up becoming 1, and I have 0 times sine plus 1 times cosine or cosine, okay? Now, that winds up being pretty easy in terms of figuring that out. And once you see it a couple of times, it actually winds up being pretty easy to reproduce it. Not that I'm saying that you ever will be asked to reproduce it. By similar fashion, I can actually show that cosine winds up being equal to negative sine, okay? And so that's because, remember, the sum formula for sine is a sum. The sum formula for cosine is a difference, and that's where the negative gets introduced, and the derivative for cosine becomes negative sine x. Now, once I know that, I can actually perform the other four simply by using the quotient rule. And we're going to do that very, very quickly, and hopefully, this will actually be a relatively short video for you. If we have the derivative with respect to x of tangent x, Now some of you may remember that that's secant squared, and it is, but I want to show you why. And I think we may have touched on this in a past video, but it doesn't hurt to repeat it and to show it again. So what happens here is we have the bottom times the derivative of the top minus the top times the derivative of the bottom. Actually, this is supposed to be cosine. I'm a dope. Okay? Minus sine x, all of that over cosine x quantity squared, right? Well, that numerator simplifies to cosine squared x plus sine squared x, all of that over cosine squared x, and I'm going to get 1 over cosine squared x, and that of course simplifies to secant squared x. Now, similarly, when I have cotangent, okay, I remember that this is simply cosine x over sine x. Well, the same principle applies. I'm going to start with sine x, okay, and the derivative of the top, negative sine x, okay. Now I'm going to subtract the top, cosine x, times the derivative of the bottom, cosine x. Now notice that the sine x, negative sine x, is now in this first term instead of this second term. So whereas here it naturally cancels with this subtraction sign, it does not do so here, okay? And that is why, in order to get the Pythagorean identity in the numerator, we actually have to factor a negative out of both terms, and that is why the derivative of cotangent is negative, whereas tangent it's not. Here the negative happens to pop up in the term where it's going to go ahead and cancel with this negative, so I'm going to get positive, positive. Here, it actually winds up in the other term, so I get negative, negative, requiring me to pull this out in front, and so I have a negative 1 over sine squared, or negative cosecant squared x. Okay? Now, what we have for, and we'll go ahead and do secant. Now we can either, if you watch the video on proving the product and the quotient rule, you actually could use the reciprocal function, but we're not going to do that. We'll go ahead, for those of you that didn't watch it, and we'll just sort of grind it out with respect to the quotient rule. Okay. Now that means the bottom times the derivative of the top. Well, if I have a constant, the derivative of a constant is 0, right? Okay, well then I'm going to have the top times the derivative of the bottom. The two negatives, of course, are going to cancel out, okay? That's going to be 0. And you're going to wind up with sine x over cosine squared x. Well, that doesn't look like what I remember secant x to be in terms of its derivative. Well, all you have to do in order to actually get it into the form that you've actually seen it in before is pull it apart into its factors, and of course that winds up being tangent x times secant x, or what you're used to seeing it as is secant x tangent x, and of course that's the same thing because multiplication is of course commutative. Now let's go ahead and do it for cosecant, and then I'm going to line them all up and show you why these are really not all that bad in terms of memorization. Okay, and I'm going to make the same move here for cosecant that I did with secant, right? For secant, I merely defined it as its reciprocal function. Okay, so I'm going to take the bottom times the derivative of the top minus the top times the derivative of the bottom. Now are you starting to see why cosecant is negative? Because there's no negative to cancel out this subtraction sign right here. And so what I'm going to get is I'm going to wind up getting, of course that cancels out just like it did in the last one because anything times 0 is 0. I'm going to get negative cosine x over sine squared x, and this is going to pull apart in exactly the same way that the other one did. Just pull apart into its factors, and I should have put that in a different order, anticipating turning it into the quotients, but let's go ahead and do it in this step. The 1 over sine becomes cosecant, the cosine over sine becomes cotangent, and that is exactly what you should remember the derivative of cosecant, if you remember it at all, what you remember the derivative of cosecant to be. Now, could I actually take all 4 of these and run them through the limit definition of a derivative? I sure can, yeah, and I think I may have actually done that for tangent at some point. My object here is not to torture you with revisiting the limit definition of a derivative over and over and over again. My point here is basically showing you and just sort of demonstrating to you the fact that these are indeed the derivatives. We don't get there by magic. It's not, divination. It's nothing esoteric. These are actually defined as the derivative of the 6 trig functions for very, very good reasons. And of course, we can sort of show those reasons in a multiplicity of ways, but for our purposes right now, we only need to do it in one way. So let's go ahead and actually show those. So we had the derivative of sine is cosine. The derivative of tangent is secant squared, okay? And the derivative of secant x is secant x tangent x. Now, usually I line things up sine, cosine, tangent, cosecant, secant, cotangent. Now, why have I lined them up like this? Well, notice that these, none of them have the prefix co in front of it, right? Because co-functions, co actually means complementary, right? If you remember our discussion of that when we first introduced it and we were doing cofunction identities, sine of 30 degrees is equal to cosine of 60 degrees, meaning that the value of cosine is equal to the sine of its angle complement, right? So tangent of 30 degrees is equal to cotangent of 60 degrees. Secant of 30 degrees is equal to cosecant of 60 degrees, right? And that's how we got those cofunction identities. And that's why they have co as a prefix. So that's kind of fun. But if we actually line them up so that they are next to their cofunctions, we wind up seeing something of a pattern here that is actually going to help us in our ability to memorize these so that we don't have to spend a whole lot of time doing it. Now, you should always remember, it should be very, very easy, that the derivative of sine is cosine. So, if you just remember that, the only two that really need to be memorized are these two. That's it. Because notice that the derivative of sine is cosine. The derivative of its cofunction is equal to the derivative's negative cofunction. So the derivative of the cofunction is equal to the derivative's negative cofunction. The derivative of tangent is equal to secant squared. The derivative of tangent's cofunction is equal to the derivative's negative cofunction. The derivative of secant is secant tangent. The derivative of its cofunction is equal to the negative cofunction of its derivative. So notice that secant tangent becomes negative cosecant cotangent. Emphasis on the negative and the co. Okay? The derivative of tangent, like I said, is secant squared. Secant squared becomes, when you go from tangent to cotangent, negative cosecant squared. Okay? And cosine becomes negative sine, and sine is, of course, cosine's cofunction. Okay, that ought to actually be pretty straightforward in terms of being able to do the memorization there. So now that I've actually shown them to you, we'll go ahead and stop the video here, and I will spend probably 2 more videos just doing examples and sort of fleshing it out a bit so that you can get a grasp of what 3-3 is all about.